Water and oil don't mix, and that simple fact is central to how life works. From your brain cells to your bloodstream, your body is quietly exploiting this immiscibility every second. It's not just chemistry, it's survival. In this video, we explore the molecular forces and thermodynamic principles behind this all-important separation. By the end, you'll understand how hydrogen bonding, entropy, and energy balance explain why these two substances stay apart and why that separation matters. Water molecules are polar and form hydrogen bonds, strong electrostatic attractions between the partially positive hydrogen atoms and the electron-rich oxygen atoms of neighboring molecules. These interactions require significant energy to break. Oil molecules, composed of nonpolar hydrocarbons, interact through much weaker instantaneous dipole and induced dipoles. These arise from temporary fluctuations in electron distribution around an atom or molecule, leading to instantaneous dipoles that induce dipoles in neighboring atoms or molecules. To mix water and oil, the system must overcome the intermolecular forces within each phase, breaking hydrogen bonds among water molecules and van der Waals interactions among oil molecules. This process requires energy, an increase in enthalpy. However, the interactions formed between water and oil molecules are weak and do not release enough energy to compensate for the energy required to disrupt the original bonds. In other words, the mixing process is energetically unfavorable. To determine whether a process is spontaneous, we examine the Gibbs free energy. Delta G equals delta H minus T times delta S, where delta G is the change in free energy, delta H is the change in enthalpy, T is absolute temperature, and delta S is the change in entropy. Entropy, often described as molecular disorder, tends to increase in spontaneous processes. According to the second law of thermodynamics, systems naturally evolve toward higher entropy. At first glance, mixing oil and water might seem to increase entropy, two substances becoming one disordered mixture. However, water molecules respond by forming structured arrangements around the nonpolar oil molecules. These are sometimes called hydration shells, or water cages. This ordering reduces the entropy of the water phase. So while mixing introduces some disorder, the formation of these cages imposes molecular order, offsetting the gain. The net entropy change, delta S, is therefore small or even negative. Combined with the unfavorable energy balance, the overall Gibbs free energy, delta G, remains positive. The system avoids mixing and instead separates into distinct phases. What we've explored today is more than just a curious quirk of chemistry. It's a fundamental separatrix, a boundary that defines how matter organizes itself. The immiscibility of water and oil is a vivid example of how molecular forces and thermodynamic principles shape the physical world. In the videos to come, we'll uncover how this separation drives biological function, enables industrial innovation, and even solves real-world problems. From the architecture of cell membranes to the design of emotions and advanced separation techniques, this invisible boundary is everywhere. So stay tuned as we journey through the chemistry of interfaces, where molecules choose sides and where that choice makes all the difference.